All right. Let's continue our discussion now. Layout design. Okay. Now we got the picture of process, fabrication, packaging, etc. Now we can move towards layout. How do we make layout of a transistor? How do we make a layout of, let's say, NMOS, PMOS, then an inverter, right? How do they look like in reality? So layouts are not the side view. Okay, remember that when we are making layouts in Cadence or Unedited, right? Whatever you are looking on the screen is not the side view, but it's a top view. So from the top, what will you see? Let's say you see this screen, right? And then you will see all dots on that layout editor. So these are nothing but pixels, so which will define the minimum feature size. Okay, so if I want to say one pixel connection between one connection to another connection, this is a minimum feature size permitted by the technology. Okay, so below which I cannot go. So it depends on technology. Okay, it can be 30 nanometer, it can be 15 nanometer, it can be 10 nanometer, it can be 7 nanometer, it can be 65 nano, it can be 90 nano, 180 nano, right? Depending on your technology, these things will be decided. So if I talk about layout rules, right? What are layout rules is nothing but what is the minimum width permissible by a interconnect, right? So what does it mean? If I have a metal running from one device to another device, what should be the minimum width of this? Who will decide that? Right? It depends on the current which will be flowing through that metal, right? If the currents are high, then it will melt. Correct? So who decides the current? How much current what should be the max current which should be flowing through this circuit? That will be decided by the technology. So what is the technology? So when I say technology, technology means what is the minimum distance between source and drain? That is nothing but technology. Or I can say as channel length is nothing but technology. So when I say channel length as 90 nanometer, the technology of that design is 90 nanometer. Okay. So once you say to to the fabricator, right, they have to upgrade their process for our technology. So let's say you call them TSMC is one company, let's say. IMEC Belgium is another company. Right, there are many things. So we have Global Foundries, GF. So our own alumni works here in GF also, Global Foundries. Okay, so then there will be other IBM, etc., etc. Okay, so now these people, you call them, they say that okay, currently this month 90 nanometer technology runs are going on. So then we say that okay, our circuits are also 90 nanometer. Then only they will take in. If we say 180 nanometer, then they will say, okay, 180 nanometer will run in June, so send your designs in June. So now we say that no, I will not wait. Whatever is going on, to change it and fabricate for me. Then they will say, you have to pay the cost of whole change of process. Okay, all the settings which they have there in the fab industry, you have to pay for that. So who pay for that? Usually the big people, when they are ordering in millions, right? If they are saying that I need this circuit to be fabricated in this many numbers, right? 1 million number, or 10,000 number. 10,000 is very less. Usually they go in more than lakh or 10 lakhs. Okay. So then they change the process for them and then they do it. In that timings, they fit us, people like us, universities, when we want to do. And even then, they don't fit us for one thing. Okay, we say that I have 1 centimeter or 2 centimeter by 2 centimeter chip. Can you please fabricate? They will say that the whole wafer is of, I told you, right, around 12-inch diameter or 5-inch diameter or 4-inch diameter, right? So they will say that you have to wait until the whole plot has filled by various universities or various small startups, right? They wait for various people to fill that whole plot. So they will take order from you and then keep it on hold. Then they will keep order from another person. So this kind of multi-wafer fabrication, MWF. If you go for this will be cost effective, right? So even when we say it's cost effective, they'll still charge you $2,000 per centimeter square. Okay, that's the cost effective approach. Then your number may come after 6 months, 3 months, you don't know. So many students who do research on fabrication and these things, they have to wait. So their thesis cannot be, okay, finish my thesis, I have to go to job or I have nothing. You have to wait. That's it. So these are all processes, right? So I was talking about this. What should be the minimum width of this, right? So depending on your technology, the minimum width will be decided because the currents will be decided. So then current, what should be the VDD which should be given to 90 nanometer, to 180 nanometer, to 45 nanometer, right? So these things depends on, usually they go until 500 nanometer. At that time they used to give 5 volt. Then you went to 300 nanometer, then they start 330 nanometer, then they started 3.3 volt. So usually it came down linearly. The scaling came down linearly. But when we are going in very low now, it's not linear. They have to do some trial and error and try to find out what should be the voltage given as VDD. Okay, so when 90 nanometer was given, sorry, 180 nanometer technology came. So at that time I worked on 330 and 180. So we were using 1.8 volts. Okay, then when 90 nanometer came, so they, instead of using zero point 0.9 volt, they were using 1 volt. Okay, so I don't know, now you can look on Google what should be the VDD for 45 nanometer, what should be the VDD for 10 nanometer. I don't know, you can check those things out. So what it is telling us, as the technology is scaling down, the VDD is also coming down. Okay, when VDD comes down, the current flowing through the transistor and as a result to the conductors which we are using as metals, right, that also will come down. So as a result, the width also will come down. So who will keep track of all these things in terms of micrometer? So rules based on micrometer is one thing. Another is rules based on something called as, we have chosen one variable, that's it, lambda. So whenever your technology changes, you give some value to this lambda, automatically you will get exact micron rules for that, right? For example, I will say that the minimum width of your transistor is 3 lambda. Okay, so this is generalized rules. And then what I can do, I can give a value of lambda as 0.3 micrometer for a process of, let's say, 300 nanometer. So what will happen? So this is nothing but 300 nanometer, right? So 300 multiplied by 3, 900 nanometer should be the width of, minimum width of your metal, okay, or interconnect. Now if there are two interconnects running side by side, one is used for some other purpose, one is used for some other purpose. then we don't want any coupling between them, right? We don't want any short circuiting between them. So what we do, we need to have some rule how far they should be away from each other, right? So these kind of rules are called as design rules, and the checker which is there in your cadence is called as DRC, design rule checker. Okay, which will be sitting in your CAD tool. The rules has been feeded by, of course, human beings to check whether the designer is following those rules or not. The moment you make a mistake, then the checker will say your design has not passed DRC. DRC rule failed. Okay. So what are these rules? We will come to these rules later otherwise. Let's first design. We started our journey from these things, right? We want to make layout for these things, right? So a transistor, how does it look like? If you see from the top view, you will be having one active region running. And if you see from top view, you will see some contacts. So if you see in the side view, these contacts are this one. Okay, you need to make holes and make some contacts there. And then you will be having a gate layer running on it. Right, it looks like this. There will be gate layer running on this. Okay. So if it is NMOS, we can say for NMOS, what is the usually there before this there is, I told you I think in the last class, right? NWEL process. What we are discussing is NWEL process. In NWEL process, what will happen is your whole substrate will be P-type. So you buy a intrinsic silicon wafer, you dope it with P-type material completely. So it will be P-type. If you see this, it will be P-type substrate. So then what will happen? You just need to do doping of N-type here and then put a silicon oxide layer, then put a polysilicon, right? And in NWEL process, if I want to make PMOS, what should I do? I have a P-type. I need to make a tub called as NWEL. In that, I will be doing P-doping. Okay, and then gate it. So I have this wafer which is P-type. If I want to make NMOS, I will just do N doping on both sides and then deposit silicon dioxide in the center and put a gate poly there. That's it. If I want to make a PMOS, I need to first make an NWEL, then put P, then put the gate. Okay. So this is what we have done here. So this will be like, usually this is called as active region. That means in this area we have used for NWELs, then NWEL we have make some connections, and then we have gate. Okay. Huh? Yeah. So no, one wafer we have to put both, right? PMOS and NMOS. That's why it is called as CMOS. You cannot take another wafer. So you can go with PWEL process. It will be again same, right? You will be having N-type wafer, and then you will be having PMOS, and then NMOS, you need to make a P well then at that time, right? But usually they go with P type. Okay, and this process got more priority by more fabricators than P well process. Okay, so how does the layout looks like? This is for your NMOS. For PMOS, how does it look like? Okay, let me write NMOS here. So for PMOS, it will have a N well. Let me draw with different colors. I will have N well. Then I have a active region. This active region is now will be having P diffusions, right? And then I will have a gate. Then I can put some connections. These are called as contacts. Okay. How to make a PMOS, how to make an NMOS layout is clear. So we can do some decorations. Instead of these colors, which you cannot draw it in book, I will use black color and differentiate between each region. So we can do something like this. Slant on the right. So let's call it metal. Slant on the left. Let's call it poly. Okay. We are differentiating layers now. In your cadence or LD, edit, all those things, they will be differentiated by colors. Okay, or designs. Here we are differentiating only by design. I'm using dots for NWell. Okay. Huh? N active, P active, nothing but if I want to make an NMOS now, so I am showing it like this. Below each diffusion layer is there here and here, and diffusion on both sides. Then I will use on the left slant, that means poly, and then I will use two contacts here. This will be like NMOS. If I want to make PMOS now, and well, imagine all these things on the top, right? Then P active, which will be by vertical lines. and then I have contacts, then I have gate, left slant. This is my NMOS and this is my PMOS. Clear? So how do I make inverter now? One way to make inverter is I need to pull this and pull this. Oh, not this direction, right? Left slant is what? Yeah, poly. So I pulled a poly and pulled a poly here also. Then I will run a metal line here. The metal line will have this. And I need to make a connection between them. So I will put a drill and fill that hole with metal. So that means poly is on first floor, metal is on second floor, and I ran that on second floor, second layer, and put drills there and connected to the poly. And these drills are called, I am calling it as contacts. And these, because they are drills made for poly contacts, they are called as poly contacts. These contacts are called as diffusion contacts. Because those contacts or drills or holes are made to connect the diffusion layer. So we call it a diffusion contact. They are called as poly contact, right? Sometimes what happen is on this first floor, second floor, we are running the metal, right? I want the connection to go and connect to some other part of the circuitry. So I may need a help of another layer, because on that layer I cannot bypass certain devices. So how to go up and then go and then come back, right? So I will then called as this metal which I have used for the first time in my circuit, in my VLSI. It can come on the first floor, it can come on the second floor, but first time when I am using the lowest layer on which I am using the metal is called as M1. These symbols are given in your edit, okay, cadence, M1, M2, M3, they are all aluminum. But because they have used on the bottommost layer, I will call it as M1. Then the next layer I will call it as M2. Then the next layer I will be calling it M3, M4, M5. It can go till M24. Okay. So how do I do that? When I need to make another metal connection, and I will call it as M2, I cannot use the symbols like this. Let me use symbols exactly horizontal. In cadence or any edit, they will be differed by some colors. So this will be usually M1 will be blue color and this will be pink color. Okay. So M2. So how do I make a connection then? I need to again make a contact, make a drill and make a contact between them. Okay. These contacts are called as via. So as it is connecting M1 and M2, it is called as via1. So M2 and M3, it will be called as via2, via3, via4, via5. All these have been now again in your CAD tool will be differed by different colors or different design combination, design and color combination. Okay. So via1 only can be used for connecting M1 and M2. via2 has to be used to connect M2 and M3. Now you can ask a question, they are all holes. Why do you want to differentiate all these things, right? Let's say via1, via2 or poly contact, diffusion contact. Imagine you make a CAD complete layout and send it to the fabricator. The fabricator will open it in their system. How will they know if all are equal? You are not differentiating. They are all holes, 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 holes. How will they know which hole is for which layer? Therefore, we have to differentiate between the holes. This hole is for ground floor. This hole is for first floor. This hole is for connecting second floor and third floor. Clear? Yeah. We have one. That's it. So now you can say that this M1 and M2 we have one. Now I will have another layer, another circuit on the same floor, which is having M1, and I am connecting this. So this will also be via 1 only, because this is telling the fabricator that these holes are made on the second floor to connect, sorry, between second and third floor. Okay, clear? Yeah, so we connected the gates now. Now what else we need to connect? So now this drain and source, which one is left drain and which one is source, left or right? Right, is this drain and this source, or this is source, or this is drain? It's open, right? It's we who decide that, because they are more same. It depends on the connection which you are giving. It's calling it as drain or source. Otherwise, in physical structure, they are all, both are endowed, right? So I can take a decision on that. So for me, it's easier to connect this and this. So that means what? This is the drain of NMOS and this is the drain of PMOS, because drain and drain of NMOS and PMOS has been connected. Correct? So I will again do the different connection I need to do to connect this drain. So the best way is I can make another connection here. Some metal I run it here, and then I can connect it like that. Or I can directly connect one metal line here. That's it. Connecting to the drain. Okay. Then I need to make this connection with metal again, and then this connection with metal again. This I will connect it to ground. This I will connect it to VDD, and then I will have to draw the pads, right? Pins or pads, whatever. Here also I need to, so I'm connecting, let's say I want to connect the input through M2. So I'm designing a pin here. I can connect, I can say that why should I go to another layer, waste of money, right? So I can delete all these things and have a pin here itself, right? Or I can do like this. This hole is metal one only. And use this part as a pin to connect my input. I need to check the output. Here I can check the output. Connect directly on the metal one pad, one pin, right? Then it will be my out. Right? So we'll continue the discussion in next class. How to make it simple. This looks messy, right? What should be step-by-step approach to design our own layout? Okay, in the next class. Any doubts? Oxide, not silicon, oxide. Every layer has to be separated by insulator. Otherwise, there will be short circuit. Right?